Whole body suits were introduced back in 2008. These suits led to break around 200 world records only in 1 year. The secret was a significant increase in buoyancy and speed provided by whole body suits.
Our hypothesis is that swimsuits should reduce the amount of drag and result in faster swimming speed. In our analysis, we'll be using two equations, the force due to drag, utilizing the density, the area, the drag coefficient, and the velocity, and Reynolds' equation utilizing density once again, velocity, the length of the swimmer, and viscosity.
So the swimsuits work on reducing the drag force between the swimmer's skin and the water. They focus on the drag coefficient, and to reduce that term, we need to decrease the viscosity. Why do we need to do that? That is because the Reynolds number, which determines the drag coefficient, is dependent on the viscosity. So when we reduce the viscosity between the swimmer surface and the water, we increase the Reynolds number, and when we increase the Reynolds number, we decrease the drag coefficient, which in turn decreases the drag force that is being applied on the swimmer and the water. This decrease in the drag force leads to faster times and better swimmers.
Next, we will be talking about why golf balls have dimples. Our observations are that a smooth ball goes about half as far as a dimpled ball because of the laminar flows. Our hypothesis is the dimples reduce the drag around the ball and make it fly further. The dimples create a turbulent boundary layer that reduces the wake behind the ball.
To analyze this phenomena, we will primarily be using the Reynolds number equation, which uses the density of the air, the velocity of the ball itself, the diameter of the ball, and the viscosity of air. The various dimple pattern designs of the golf ball create turbulent flow early on, and this in turn allows the velocity of the ball to be greater, the coefficient of drag to be less, and will allow the ball to travel further due to the lack of resistance. When this thin turbulent boundary layer is created, this makes a ball more efficient due to the fact that air is flowing smoothly over the contours of the dimples and creating a smaller tail end wake. Since the flow is turbulent, not laminar, the Reynolds number is higher, which in turn relates to a higher velocity of the ball since the density, diameter of the ball, and viscosity all remain the same. The ball also travels farther due to the fact that pressure is higher at the stagnation point at the head and less towards the tail end of the ball, creating a smaller wake area towards the tail. A dimpled ball also has about half the drag as a smooth ball due to this phenomena. Dimples also affect the lift by creating backspin, which warps the airflow to have higher pressure on the bottom of the ball and less on the top, thus creating an upward force in the ball, which will allow the ball to travel even further.